So welcome everyone to this session of numerical solving and example solving session on transformer. In today's session we are going to solve examples based on open circuit test and short circuit test. So let's begin with the example number 1. So we will start with our green pen. So we'll write whatever the data is given to us. The following are the test results of 10 kVA. So this 10 kVA is the power rating of transformer. So we will write P is equal to 10 kVA, 1100 by 440 volt single phase transformer. That means primary voltage V1 is 1100 volts and secondary voltage V2 is equal to 440 volts. Now the open circuit test, so the data of OC test. So the data of OC test is normal primary voltage and power is 500 watt. So 500 watt is the data from the open circuit test. Then short circuit test from SC test we can write from the numerical given to us. The power loss calculated in SC test, it's 850 watt and the voltage measured is 40 volt. When the secondary winding is shorted and full load current is flowing. So in short circuit test condition, the full load current is flowing. So that is given to us. Now what we need to find? So data to find. So what data we need to find? The data we need to find is find full load efficiency. So we need to calculate efficiency and regulation at 0.8 power factor. So voltage regulation we need to calculate at 0.8 power factor. So this much of data is given to us, and now we are going to solve example using this data. So let's begin with the solution. So how we can solve this example? So first of all, what do we need to find? Let's write the things that we need to find. First we need to find efficiency. So the equation for efficiency is output divided by output plus losses. But we have two specific losses, iron loss and copper loss. So to calculate the efficiency we require first of all output. So how to calculate the output? So let's write the equation to calculate the output of the transformer. Output of transformer is equal to kVA cos 5. So we need to calculate the efficiency and voltage regulation. See, find full load efficiency and voltage regulation at 0.8 power factor lagging. So this is key data for us. So the power factor is given to us as 0.8, and the kVA, that means full load rating, power rating is also given to us. We have written over here, it is the full load power rating, right? So it's 100 kVA transformer and the power factor is 0.8. So obviously it is 80 kilowatt. So the output of this transformer is now known to us, and that is 80 kilowatt. the data given in OC test, that is 500 watt. This 500 watt is nothing but the iron loss, and this 850 watt is nothing but the copper loss. So we have the iron loss and copper loss amount which is given in the example, but these two amounts are in watts, so we need to convert it in kilowatt and write. So the output we have got 80 kilowatt divided by 80 plus it's a 0.5 kilowatt plus it is 0.85 kilowatt. So now let me calculate this. Uh, 80 plus 0.5 plus 0.85 gives us 81.35. So 80 divided by 81.35 gives us 0.9834. So 0.9834 is the efficiency, and when we convert this efficiency into the percentage, we need to multiply it by 100. Once we multiply it by 100, we get 98.34%. So this is the first finding from the SCOC test, and it's very good that Saurabh and Parth has calculated it the correctly. That's very good. I appreciate your efforts. Even Kamlesh has also calculated it correctly. So now the efficiency is known to us, and the next thing we need to find is voltage regulation. So ultimately we need to find percentage regulation. So what is the equation of percentage regulation of transformer? The equation for the percentage regulation when the power factor is lagging is I1 R01 cos 5 plus I1 X01 sin phi divided by 0V1, that means no load voltage, multiplied by 100 because we need to calculate this thing in percentage, right? So that's good. Even Kothari, Parth and Kamlesh and Saurabh, you all have calculated the answer correctly. Now what we need to do, we need to place the values, right? So to place the values, we require these things. Do we know R01? Is R01 is known to us? No, R01 and X01 is not known to us. So first we need to calculate this. But is the I1 is known to us? No, I1 is also unknown. So we need to calculate the I1, we need to calculate the R01, X01, sin phi, because cos 5 is given to us, that is 0.8. This quantity is known to us, 0.8 lagging power factor. So from this we can calculate sin phi, and V01 is the primary voltage. So the quantities which are marked with yellow marker, that quantities we need to calculate. So what we will do, first of all we will start with calculating I1. So we will place all the values once we are aware with them. So first of all let's start finding I1, and from where we can find I1? I1 is the primary current. So see, SC test is performed at full load. SC test is performed at full load. So secondary is shorted and primary is flowing the full load current. So if we calculate the full load current using this copper loss, it's easy for us, right? So the equation for copper loss, WC, is I1 square R01, right? So to calculate this is the equation for copper loss, but this will not gives us the current. To calculate the current, we need to use the equation of transformer. KVA is equal to V into I. So KVA is power rating of transformer, it is V into I. So if we divide it by 1000 and divide this also by 1000, so that will balance the equation, right? So now let me get the values. KVA rating of the transformer is 10 kVA. So it is 10 in kVA. So what we'll do, we'll multiply it by 1000. So it will become into VA. Voltage is given to us as 1100 and I1 current that we need to find. So from this we can write that I1 is equal to 10,000 divided by 1100. And when it is 10,000 by 1100, it's simple to calculate. Just place the values in calculator. 10,000 divided by 1100, and that's it. It's 9.09, right? So let's go for this. I'm sorry, it's 100 kVA and I have mentioned over here only 10 kVA. So that's a mistake. It's 100 kVA. So over here there will be one more 0, and in this point will be shifted on right hand side. So we'll get not 9.09, but we will get 90.9 ampere of current. So that's good. Kamlesh, good. Parth, good. But I did that small mistake in writing the data, so the answer is slightly a different one. But you can correct it right now and you can carry on the same thing with me. Okay, so good. You have updated it. Good, Kamlesh. So now as we are ready with I1, now we can calculate the remaining thing. Now we know the I1. Now we'll go for the R01, right? So we are now finding R01, and to calculate R01 we are going to use the equation of copper loss. WC is equal to I square R, and that is I1 square R01. So as we want to find R01, we'll rearrange the equation like this. So this WO or WC is 850 watt, right? It's 850 watt divided by I is 90.9 square. So let us calculate. 90.9 into 90 point, sorry, 0.9, 8262.81. So 850 divided by 8262.81 gives us 0.1028. So it's 28, so we'll take it as 3, so 0.103. So 0.103 ohm will be the value of resistance. So now the resistance is known to us, R01, it's known to us, and now we'll go for the X01. See, do you remember this equation? Z is equal to under root R square plus X square. So this is known to us. If we calculate this using this equation, we can calculate the X. And to calculate the Z, it's very easy. Why? Because we can use this equation. Z01 is equal to, Z is ultimately the impedance. So impedance is volt by current. So VSC, right, short circuit voltage divided by the current at short circuit time. And what is short circuit voltage? the short circuit voltage is given to us is 40 volt. So we'll use VSC 40 divided by IT is 90.9. So 40 divided by 90.9 gives us 0.44. So this equal to 0.44 ohm. So now the Z is known to us. Very good, Saurabh. Good work. So now the Z is known to us, that is 0.44 ohm. And if we place the value of Z over here, we can get X01 is equal to under root Z01 square minus R01 square. So Z01 is 0.44 square minus R01 is 0.103 square. So 0.44 into 0.44 gives us 0.193. So this is 0.193 minus 0.103 into 0.103, it's 0.0106. 0.0106. So 0.193 minus 0.0106 gives us 0.1824, and under root of this is 0.427. So now the X01 is 0.427 ohm. So now this quantity is known to us, X0, R0, right? So we know I1, we know R01, we know X01, right? Now we need to calculate the sine 01. It is very simple, that you need to remember this. When cos 5 is equal to 0.8, sine 5 is equal to 0.6. And let me show you the process to calculate this. If you want to calculate this thing, that how when the cos 5 is 0.8, sine 5 is 0.6, then you can follow this procedure. Phi is equal to cos inverse of 0.8, and using this you will get phi angle, right? So sine of this angle will give you the value of sine, and that will be equal to 0.6. So this is how you can calculate this thing. Good, Saurabh. Good work. What about other participants? Limited participants are responding today. Is it anything wrong with you all? What happened? So now we'll write the equation for regulation again. Percentage regulation. The equation for that is I1 R01 cos 5 plus I1 X01 sine 5 divided by 0V1. I1 is 90.9 multiplied by R01 is 0.103 multiplied by cos 5 is 0.8 plus I1 is 90.9 multiplied by X01 is 0.427 multiplied by 0.6 divided by 1100. This 1100 is the primary voltage, this one. So now our task is to calculate this thing. So let's solve this thing in a small steps. First we'll calculate 90.9 multiplied by 0.103 multiplied by 0.8, and that gives us 7.49. So we'll take it as 7.5. 7.5 plus 90.9 multiplied by 0.427 multiplied by 0.6 gives us 23.288. So we'll take it as 23.29. So 23.29 divided by 1100, and that gives us plus 7.5 divided by 1100, that is 0.02798. So we'll take it as 0.027 or 28, 0.028. So it's 0.028. It is percentage regulation, so over here we need to write multiplied by 100. Over here also it's multiplied by 100, and over here it's also multiplied by 100. So finally we get the percentage regulation is equal to 2.8%. So this is our another finding. So this is how you can calculate the percentage regulation and the efficiency of the example. Just go through this example. This is the solution of this example. So that's it. If you have any query, you can ask in comment section. And now we are shifting to the next example. And before moving to next, there are several participants who are answering the answer. Saurabh, Parth, Anish, Jairaj, very good. Good work, all of you. So now let's start our example number 2. Let's take our green pen and write data given. So whatever the data given to us as, the following are the test results of 5 kVA. So the rating of transformer is 5 kVA. P is equal to 5 kVA. Primary voltage is 400 and secondary voltage is 200 volt. And a single phase transformer has OC test of this much. So let's write V1 as 400 volt and V2 is equal to 200 volt. The data from OC test. So voltage from OC test that we are getting is 400 volt, right? The current is 1 ampere and power is 50 watt. This is from HV side, right? And the next is SC test. So we'll write the data of SC test. The voltage is 12 volt. The current I is equal to 12.5 ampere. Sorry, it's not volt, it's ampere. And the power is 60 watt. And this data is also on HV side. All these are, very important information to write, because the data is from LV side or is from HV side. HV side, that means it's from high voltage side, so all the data is referred to this primary side, because our primary is of high voltage. So all this data is referred to the primary side, right? So this much of things should be clear to you. And now we'll find out full load efficiency. So we will write over here data to find. What we need to find? We need to find full load efficiency and regulation, percentage regulation, and these things at 0.8 power factor lagging. So at 0.8 power factor lagging, we need to calculate these things, right? So now let's go for the solution. Now let's go for the solution. So first of all, let's write what we need to find. It's very simple. We need to calculate the efficiency, and we all know the equation for efficiency. Efficiency is nothing but the output divided by output plus iron loss plus copper loss. Now let's go for what do we know and what do we need to know. So the output is not given to us, right? Output is not known to us. We need to find the output, the iron loss and copper loss. The open circuit test gives us the iron loss and the short circuit test gives us the copper loss. So we can write Wi and Wc. So we have the iron loss and copper loss data with us. So we do not need to find these two we are having with us. So first of all, we need to find the output. So how to calculate the output? To calculate the output, it's not a big task, right? What we can do is just use the equation of output. Output is equal to kVA cos 5. Full load kVA of transformer is 5, so it's 5 kVA multiplied by, we need to find this efficiency at a 0.8 power factor. So definitely we are going to use this 0.8 power factor to calculate the output. And it's 5 kVA, 5 into 0.8, it's going to give us 4 kVA, or sorry, 4 kilowatt. It's 4000 watt, or you can write 4 kilowatt of output. So now the output is known to us, so we can calculate the efficiency. Output is 4 kilowatt divided by 4. Iron loss is 50 watt, right? So 50 is 0.05 kilowatt plus 0.06 kilowatt. So it's 4.1. So 4 divided by 4.1 kilowatt gives us 0.9756. And if we want to convert in percentage, so we need to multiply it by percentage. So we can directly write 97.56. So the efficiency at full load is 97.56%. So that's quite a good amount of efficiency. And you know that amongst all the electrical machines, the highest efficiency achieved by any machine, that is transformer, right? Because it does not contains any rotating part. Now we'll move to calculate voltage regulation. So the next section is percentage regulation. And what is the equation to calculate the percentage regulation? I1 R01 cos 5 plus I1 X01 sin 5 divided by OV1. That means our supply voltage or no load voltage. So now let's check what do we have and what do we need to calculate the percentage voltage regulation. The current is not given to us, right? So that we need to calculate the I1 current, we need to calculate R01 X01 sin phi, because this data is not given to us, right? Now cos 50 and supply voltage. So this green data is known to us and this yellow data that we need to calculate. So before calculating this percentage voltage regulation, we'll go for this individual quantities I1, R01, x01 and sine phi, right? And then we'll place all the values in percentage regulation. So what we'll do, we'll divide this section into two part, and from the right hand side part we'll start calculating the I1. So now we are calculating the I1. So how we can calculate the I1? The kVA rating of transformer is known to us. So it's ultimately V1 I1 divided by 1000. What is kVA? The transformer is of 5 kVA. The supply voltage V1 is known to us, and that is 400 volts. So we can write I1 is equal to 5 kVA. So we'll mention it as 5000 VA divided by 400 volt. So 5000 divided by 400 volts gives us 12.5 amps. So the I1 is equal to 12.5 ampere. So this is our I1 current. Oh, very good, RD, welcome, and very good, Rishikesh Dubey. You have okay. I am back now. There was internet issue, but I am back now. So good work, Saurabh, Mananshu, and Sonu. That's good. Now again I am back. So to calculate R01, the equation for copper loss is nothing but the I square R loss, right? So it's I1 square R01. We want to find R01, so that gives us WC divided by I1 square. And what is amount of copper loss? Copper loss is 60 watt, right? So 60 divided by the square of 12.5. So this is the square of 12.5, right? So 12.5 into 12.5, we will get 156.25. So 60 divided by 156 point, it was 156 point, what it was, I forgot. Just a minute, let me calculate it again. 12.5, sorry, 12.5 into 12.5 gives us 156.25. okay, 156.25. 60 divided by 156.25 gives us 0.384. So 0.384, that is the value of R1, 0.384 ohm. So now we know the I1, we know the R01. Now we go for the next quantity, that is X01. X01. Let's calculate it. How to calculate X01? It is simple to calculate X01 using this equation. Z is equal to under root R square plus X square. So for that, first we'll go to find Z, and Z01 is equal to nothing but the impedance referred to primary side, and that is voltage divided by current. So the voltage we can get from the primary side during short circuit condition, that is 12 volts. It's VSC divided by I1, 12 volts divided by 12.5. So definitely Z is less than 1. 12.5, it's 0.96, 0.96 ohm. So now we know Z01, so we'll use this equation. X01 is equal to under root Z01 square minus R01 square, and that is equal to Z01 is 0.96 square minus R01 is 0.384 square. Now let me calculate. 0.96 into 0.96 gives us 0.9216. 0.9216 0.9216 minus 0.384 into 0.384 gives us 0.147. So we'll take it as 0.15. 0.15. So now 0.9216 minus 0.15, this is 0.7716, and under root of this gives us 0.878, so it's 0.88. So x01 is equal to 0.88 ohm. So now we know this much of quantity. Now we'll go for sine 5. You all are very much aware that when cos 5 is 0.8, sine 5 is 0.6. If you still have any doubt how it is like this, in previous example I have explained the same thing. You can go there and calculate it. So whatever quantity we require to calculate percentage regulation, that we know now. Let's place all the values and calculate the percentage voltage regulation. The current is 12.5 ampere. 12.5 multiplied by R01, that is 0.384 multiplied by 0.8 plus 12.5 multiplied by x01, that is 0.88, and sine 5 is 0.6, divided by the primary voltage, and that is 400 volts. So it's 400. Now let us calculate this thing. 12.5 into 0.384 into 0.8 gives us 3.84. 3.84 plus, good work Parth, Janish, Sonu, Saurabh, you got it right. So 12.5 multiplied by 0.88 multiplied by 0.6, that gives us 6.6. 6.6. So 6.6 plus 3.84 gives us this, divided by 400 gives us 0.0261. Right? As it is percentage regulation, we need to multiply it by 100, and the answer is 0.0261, and we are multiplying by 100, so it's 2.61%. So percentage voltage regulation is 2.61. So this is how we can calculate the percentage regulation, right? So what about you all? How many of you have got this percentage regulation correctly? Is there anybody is calculating it with me? Please write the answer in comment section if you are calculating it with me. So this is our example number 2 of our today's session. Just go through this, and if you have any query, just ask me in comment section, and we'll quickly jump to our example number 3. Okay, good. Sonu, Saurabh, Amit, Parth, good one. So let's begin the example number 3 and the final example of our today's session. This is our last example in this session. Given data, the data given to us is the following test results of 230 by 600 volt. So the V1 primary voltage of this transformer is 230 volt. V2 secondary volt of this transformer is 600 volt. Single phase transformer. The power rating of this transformer is 7.5 kVA. So it's 7.5 kVA. Ossi test. The data get from Ossi test is the voltage is 230 volt. V is 230 volt, I that is 1.2 ampere, and the power that is 280 watt. But this data refers to LV side, that means low voltage side. And now we'll calculate it for SC test, short circuit test. So the data from short circuit test is LV side is shorted and V is equal to 26 volt, I is 11 ampere, losses is 155 watt, and this data is referred to HV side. See the difference over here. The data given over here, that is referred to LV side, and the data given here is referred to HV side. So definitely this example is going to be little bit trickier one. And now we need to find, we will write data to find. What data we need to find? Full load efficiency. Okay. So now the internet was disconnected for short period of time, but now I am back again. It was just an internet connectivity issue, but I am back again. So now let's start with the solution. So first of all, we'll write what we need to find. We need to find the efficiency, and now I think you okay, so I am back again. So there was some issue with the internet. Now I am back again. So let's begin the session again. So the voice is clear. Is my voice is clear to everyone? If it is clear, then please say yes in comment section so that we can move further quickly, because we have already taken a much amount of time and we do not want to waste our time. So please say yes quickly so that we can move further. Okay, so thanks for your responses. Now we'll move further with the equation of efficiency, and you must calculate this example with me, because this one is a little bit more trickier than previous one. So please continue it with me. So let's begin. So the equation for efficiency is output divided by output plus copper loss plus iron loss. So the output we need to calculate, so we'll do it very quickly, because in previous two examples we have seen this process. So output is kVA into cos 5, right? You should arrange the bike. Output is equal to kVA into cos 5. What is the kVA rating? kVA rating is 7.5 kVA, and cos 5 we need to calculate the efficiency at 0.8 power factor. So 7.5 into 0.8. Who is calculating it with me? Please answer. 7.5 into 0.8 gives us 6. So 6 kilowatt is the load, output. So we know the output, that is 6 kilowatt. Now copper loss and iron loss. But over here, let us check. One of the data is given is referred to the LV side, and one of the data is given to us referred to the HV side. So when this type of conditions with us, first what we should do is, this is our iron loss, right? This is clear. But this is our copper loss, but is it at full load? That we need to verify. If it is at full load, then that's fine, but if it is not at full load, we need to find the full load copper losses. So how we can do this thing? And for this, first of all, we need to calculate the full load current. So full load current, that is kVA is equal to V1 I1. So I1 is equal to, what is kVA rating? It's 7.5 kVA, so 7500 VA divided by the primary voltage, that is 230 volt, right? The primary voltage is 230 volt, but the reading we are getting here, this is referred to the HV side, and we want to calculate the current referred to the HV side, and the voltage of HV side is 600 volt. So in this example, the voltage we are going to take is 600 volt, because we want the current of that HV side. And why we want the current on HV side? Because we want to know the copper losses side, and copper losses is this test is did in referred to HV side, and that is why we are referring to HV side. So this is the trick in this example, and this is good one. So 7500 divided by 600 gives us 12.5 ampere. So full load current is I1 is equal to 12.5 ampere, and what the current given to us over here is 11 ampere. So this loss, this is the copper loss, ultimately WC, right? This WC is not full load copper loss, and when we want to use this equation, we need to use full load copper loss as well as full load iron loss, but this is not full load copper loss, and that we come to know using this equation, right? So the full load current is now known to us. So now we need to find first full load copper loss, WC full load. And what is the equation to calculate full load copper loss is? It's the amount of current I and the amount of power. So the ratio of this the amount of current that we need to calculate, the amount of current that we need to calculate the copper loss, and the amount of current which is given to us. So that is 12.5 divided by 11, the square of this gives us this factor, 12.5 divided by 11 whole square, and the copper loss is 155, so it's multiplied by 155. We have seen this equation in our many previous examples, so this equation is not new to us. So now 12.5 and 12.5 divided by 11, that gives us 12.5 divided by 11, that gives us 1.136, so it's 1.14. So 1.14 multiplied by 1.14 gives us 1.299, right? So it's 1.3 almost. So sorry, 1.3 and multiplied by 155, so it's 201.438. So 201.438, so we'll take it as 44 watt. So WC full load copper loss, so this is the amount of full load copper loss that occurs in the transformer, right? So now we have the amount of full load copper loss as well as full load iron loss. Very good, Saurabh, you have got it right. Now place the values. The output is 6 kilowatt divided by 6 plus copper loss is, it's in watt, so if we convert in kilowatt, it's 0.201 plus iron loss is 280 watt, and if we convert it in watt, then it is 0.28. Sorry, it's in watt and convert in kilowatt. So 0.201 plus 0.28 plus 6 gives us 6.481. 6 divided by 6.481 gives us 0.9257, so it's 0.926, right? 0.926, and we want to calculate the efficiency in percentage, so we need to multiply it with 100, and when we multiply it with 100, we will get percentage efficiency, and that is 92.6%. So this is how we can calculate the efficiency. So now we know the efficiency. We want to know the percentage regulation. So the equation for percentage regulation is I1 R01 cos phi plus I1 x01 sin phi divided by 0V2. Why 0V2? Because copper loss is corresponding to this secondary side. That is why we are going to take the voltage on secondary side. So now for that we need to calculate everything referred to secondary side. So it's not R01, this will become R02 and this will become X02. So this is a lot different than the previous one, right? Why we have taken this? Because the copper loss we have calculated over here, it's referred to secondary side, and if it is referred to secondary side, then WC is equal to I2 square R02. So the resistance we are going to be able to calculate, that is also going to be referred to secondary side, and that is why we are writing this equation referred to secondary side. Okay, so now let's calculate the R0 using this equation. R02 is equal to WC divided by I2 square. The WC is 155 and I2 square is 11, because at this much of power loss the current is given to us, that is 11 ampere. So 155 11 into 11 gives us 121. 155 divided by 121 gives us 1.28, right? So it's 1.28 ohm. 1.28 ohm, it's R02. Now we will go for Z02, because from Z02 we will calculate X02. So Z02 is VSC divided by I2, and short circuit voltage, it's 26 volt and the I2 is 11. So 26 by 11, and that gives us 26 by 11, 2.36 ohm. So it's a Z02, and then after we'll go for X02, which is equal to under root Z02 square minus R02 square, and that gives us 2.36 square minus 1.28 square. So I will calculate this thing in calculator and directly writing the answer, and that is 1.98 ohm. Why I have not calculated in this? Because it will take a little more time and we are running out of time, that's why. So X02 is 1.98 ohm. So all the quantities that we require is now known to us. So let's place the values. Current is 12.5 multiplied by R02 is 1.28 multiplied by cos 5, that is 0.8, plus 12.5 multiplied by X02 is 1.98 multiplied by sin 5, that will be 0.6, because whenever cos 5 is 0.8, sin 5 is 0.6, and V02 is the voltage referred to HV side, that is 600. Very good work, Saurabh, Kamlesh, Jairaj, Prince. Saurabh, good work. And now let's calculate this thing. 12.5 into 1.28 into 0.8 gives us 12.8. So it's 12.8 multiplied by plus 12.5 multiplied by 1.98 multiplied by 0.6 gives us 14.85 divided by 600. So it's 12.8 divided by 600, that gives us 0.046. 0.046, and as it is percentage regulation, so we need to multiply it by 100, and when we do this we will get percentage regulation as 4.6%. So this is how we can calculate the percentage regulation, right? So percentage regulation and the efficiency that we know. So we know the percentage regulation and efficiency. So this is how we can calculate this example, right? Now there is the final section, that is question for you. These are the two examples, 1 and 2. You need to calculate these two examples by your own. Very good, Kamlesh, Manansu, Jairaj, Saurabh, Prince, you all have calculated it correctly. So these are the two examples which you need to calculate and write the answer in comment section.